So we're going further, and I would like to welcome you, our next speaker, Rikyu Yao from University College of London. Hello,
Hi.
hello,
Hi, nice to meet you.
and we will continue the energy topic. So welcome, and here we go.
Okay. Welcome to my presentation. I'm presenting with the topic of agent-based energy flow simulation of integrated energy system. I'm Richu Yao, a graduate research student at UCL. I'm supervised by Dr. Yukun Hu. And this is the agenda for my presentation. First, I will briefly introduce our research team, and I will provide a general overview of the current energy system transitions, and as well as the challenges we spotted to achieve such a transition. Then I will demonstrate this project objectives, the model details of my logic model, and demonstrate the result and some future model developments. I'm from UCL Infrastructure System Institute. In such research team, our mission is to provide better understanding of how infrastructure enables both service providers such as grid operator and users like normal households innovate to provide better critical service. We're primarily interested in agent-based and object-oriented modeling, but we also embrace both qualitative data so that we can achieve the mixed method approaches. This style will demonstrate some brief overview of energy system transition. So, as we all may aware, to fight with climate change, it is very necessary to decarbonize our society. Some key government bodies already set goals to cut emissions. For example, the United Kingdom already set targets to reduce emission by 78% by 2035 compared to the 1990 levels. Also, the European Union nationally determined contributions set a long-term climate stabilization target that this committee wants to hold the global warming at well below 2 degrees. In terms of decarbonization of the society, the energy sector is very important because research have demonstrated that the emission reduction will dominate up to 2030 in energy supply sectors. We also, other than the objective of decarbonization, we also see quite exciting technology advancement in our society. First, we can see the distributed energy generation units, the wider adoption of such technology, such as the rooftop PV or distributed wind turbines. Also, we can see that there's more interaction between different energy subsystems through the distributed generation technologies. We have the combined heat and powers, heat pumps, and air conditioning devices. Such a system and units could foster the tighter interaction between the energy systems. And also we can see that energy system will have better or tighter interaction to other systems through the more adoption of electric vehicles or the hydrogen fueled vehicles. Um, Regarding the trend of energy system transition, there is an idea emerged called integrated energy system. As we can see on the right-hand side, this is a system diagram of the integrated energy system. Such a system will integrate the renewable energy generations and the transportation sector to such a system. And also they will integrate not only one energy vector, but also multiple energy vectors, such as we have electricity, natural gas, and the thermal flows. And also in line with the concept of the smart energy grid or intelligent energy grid, the more integration of the information communication technologies will help the grid operator to better operate and optimize the system. However, in order to achieve such an integrated energy system, we have a few challenges lies between us. The first is we need to combine the simulation of the multiple energy vectors, because traditionally each energy system is analysis in a separate or individually. They don't consider really to consider interactions between the different energy subsystem. Therefore, we need a new analyzing method for this future energy system. although there is a gap in the, and particularly in the agent-based modeling methodology that we application in the network level energy system. There is quite extensive studies of how the agent-based modeling could apply to, for example, the building level system, the heating, ventilation, air conditioning system, how to operate and optimize the system, and also the community level microgrids, the decentralized operation of microgrids by using agent-based modeling is very extensively studied. And the limited study of agent-based modeling application on network level, they mainly focus on applications on particularly technologies such as sensors or communication protocols, and also to evaluate the reliability of the energy network by using the agents. So this project, we want to further develop the previous published agent-based modeling for the multi-energy networks, and also we will experiment the multi-energy flow simulation with real-world case study data. In terms of the platform for simulation, the reason why we choose AnyLogic, because it is a complete software package that dedicated to agent-based modeling. Also, it has a very user-friendly interface, and we can also integrate our Java package to the agent-based modeling very easily. Here we'll demonstrate some model details. The project of this, the objective of the project is to simulate the energy flow. Energy flow is to describe the states of energy networks. We have the flows from one node to other nodes in the network. For example, by the energy flow analysis results in electricity networks, we can know the magnitude and phase angle of voltage at every bus or node, and active and reactive flowing through each edge. The energy flow analysis is particularly important in terms of, because from the grid operator, we can know how we can better planning the grid extension, and also we can determine the best operation of existing systems. By this multi-energy network, we have to define the type of the bus or node in such a network. We have defined in this model, we have to follow the classic power system definition. We have three types of bus in this system. The first is slack bus. The slack bus serves to balance active and reactive power in this system. It behaves like a source or sink to balance the whole systems. Also, we have control bus, or called PV bus. It is really the bus where we are connected. It is connected with generators. Also, we have load bus or PQ bus. This bus actually is collect with loads for households or industrialized plants or the commercial buildings. To in line with the integrated energy system, we need to integrate multiple energy vectors into such a system, so that we adopted the energy hub concept, which was introduced by Guido and Anderson in 2005. There's a systematic diagram of energy hub shown on the right-hand side. The such energy hub is kind of makes the energy vector system where they have three features. We have multiple energy input, multiple energy output, and then the energy could convert to other energy vector in a system and storage accordingly, so that our multi-energy network is modeled by a group or a system of interconnected energy hubs. Our model is developed by the basis of the graph theory, so that at each node, every node have to follow the conservation laws, which means that the flow, as shown in the equation 1, every flow injection into the node must be balanced to the outflow at this node. Then we can further develop the equation 1 to equation 2 in a network level, where we have a system flow a matrix of flow injection of each node, then that will equals to the Laplacian matrix times a cross variable matrix. In terms of the power electricity systems, such Laplacian matrix is also regarded as admittance matrix, and across variables for electricity networks, it's the complex voltages at each node. So the calculation of energy flows follow such mathematical backgrounds for electricity networks. Well, the bold characters actually representing the complex numbers as introduced in the alternative current energy systems, so that the flow intensity, equation 3 defines the flow intensity, and then by substituting the the flow intensity in the equation 4 to the equation 3, we use the equation 5. It is how we compute the complex voltage value at bus I. Then in terms of the pipeline networks include the district heating networks and also the natural gas network. The flow potential is calculated based on both upstream pressure and downstream pressure. And the KMN actually represent the properties of the pipeline networks. It include the property of pipelines and the fluid. Then the calculation of energy flow in electric system, it is implemented with Gauss-Seidel method. So essentially, such an algorithm is computed by agents in a decentralized manner, in where each agent computes the complex voltage Vi at ith node. Then such a complex voltage value will pass to the next agent as actual value. So then the next agent will compute the new voltage value V I plus 1 at the next agent. So that by aggregating the all agent computation result, we can emerge the behavior of a whole network. For pipeline networks, we actually mimic the calculation result, how we calculate the electric power flow method. With the changes not the complex voltage variable, but the potential at each node. However, the computation of pipeline networks is simpler compared to electricity network, because we don't have complex variables. Every variable in pipeline networks are real, and we have only slack type generator. This model is conducted by data obtained from published articles. For electricity networks, we have IEEE 30 nodes network, and we also have the gas 20 nodes network and 14 nodes district heating network. From these published articles, what we want is the type of the bus, whether it is the configuration, basically the configuration of the network, whether the bus is PQ bus or PV bus, and the associated active power and the reactive power of each node. This slide shows the simulation results of the multi-energy or integrated energy system. As an example, in the node 1, we can see it is slack tab for the slack bus for the whole electricity system, where the node 3 actually is both the slack generator for the both gas and water network. In such a network, we modeled the electricity network in red lines and the natural gas in green lines, and also the district heating in blue lines. So that, as I mentioned in previous slides, what the input of the model is the type of the bus at type of the bus. For example, at the node 13 we have the PV bus, where at the node 12 have the PQ bus. So that by input all the variable from the existing case studies, then we can compute every the active power, reactive power, the magnitude of voltage, and the phase angle of the magnitude. The simulation results showed at number 5. We can see we have the apparent powers and the complex voltage values, as well as the flow potential for gas networks, as well as district heating networks. So that in the future, this we have some ideas of how we further want to develop this model. This model currently is from static input because we have the case study, we have the static, the active power and reactive power. In the future, we want to more integrate the more dynamic energy consumption for profile into the system, such as the 24-hour energy consumption profile. Also, in the future, we want to develop this model from simulation to optimization, because we have seen that agent-based modeling has a very, very great potentials in decentralized optimization. So that in our future model, we will aim to develop in the decentralized optimization of the multi-region integrated energy system. So here is the reference of my presentation. And any questions? Thank you.
Thank you very much. Thank you. And I suggest wait for a minute for appearing any questions for your presentation from our participants. I can see that there are many viewers, so maybe they have something to ask.
Sure.
Yeah. While we're waiting, I would like to remind you just to remember to take part in our activity challenge. Visit our roundtables, discuss with other participants the topics that they stated there. Join the discussion boards. So there are also many interesting things there, and bookmark your favorite sessions, make notes, maybe some interesting insights. And at the end of the activity session, we will award 10 leaders with the Analogy Cloud subscription. So be ready and take part. Okay, I can see the questions right now. Yeah, here we go. The first question from Nicholas Fatras.
Oh, yeah. Unfortunately, currently, our model does not include the conversion of the different energy types, because currently the integrated energy system we use by the superimpose of different energy networks. But we are developing the future models to include the conversion matrix in our energy hub model. Representation have more relaxed visualizations. Yeah, that's a good question. For GIS data, yes, yeah, that's a good point. We can maybe in the future we can help. We can aim to have more realistic visualization with more households on GIS data to represent actual flow simulation of our model.
Okay, we're having some more minutes to answer some questions, so we're waiting for your activities. And as we don't have any more questions. Oh no, the last one from Simon Jessen. Thank you, Simon, for your question.
The agent actually is defined as there are actually for each network there is an agent. For example, we have gas agent and the water agent and the electricity agents. These agents will compute this agent will because as I mentioned previously, our networks are superposition of the three energy subnetworks. So that for each networks actually is a group or population of agents. And then in such agents, they will calculate this in a network, the agents will compute the energy flow in this network.
Okay, we have more questions, and may I ask you, please, before you answer, to read it out loud so that we can once again understand what was the question about.
Okay, so towards what the goals would you aim to implement implementation? How would you allow the optimization toward multiple goals, e.g. grid expansion cost, maximum local autarky, carbon dioxide displacement? So to implement the optimization, we want to actually implement the decentralized optimization algorithms. Through the multiple goals, we have the multi-object optimization method. In the future, yes, it is a very popular in the research fields now. The optimization usually not only consider the reduction of the cost, but also the climate change. So in the future, the decentralized optimization, we will have a multi-objective optimization to include in our whole optimization process. How did you validate your model? Actually, the model is validated comparing to individual MATLAB simulation of energy flow of each subnetwork. So that in the past, to calculate the energy flows the validate is like for each network, we run the simulations, then we have the net flow result for each network. But in our result, we have a combined energy flow simulation for every subnetwork. So we will compare the results of our model to the MATLAB result individually to validate our model. Thank you.
Okay. Thank you for your presentation. Thank you for your answers. So,
Thank you.
I would like to remind our participants one more time about the possibility to contact the presenter directly in their profile. So if you just remember any questions you didn't ask now, you can ask them privately. And join our roundtable. So we have some minutes before the next session. So you have just 7 minutes to join the roundtable. Meet other participants, communicate with them, and be back to us. So thank you very much. Thank you very much, and see you later.
Bye bye.